We tend to imagine the early universe as a quieter place, a dimmer place, a place where almost nothing had happened yet. But when the James Webb Space Telescope began looking deep into that first stretch of cosmic time, it did not keep finding a half-finished version of the reality we know. Again and again, it found signs of a universe already busy with structure, already bright in places where many people expected only the faintest beginnings, and strange enough that a Nobel Prize winner could look at the evidence and warn that we may be dealing with something that behaves, in crucial ways, like a different universe from the one our intuition prepared us for. And if you enjoy this kind of slow, reality-bending journey, stay with me all the way through and subscribe if you want more like it. Now, let's begin. The best place to begin is not with a telescope, but with a simple habit of mind. We assume that far away means far away. We do not naturally feel that it also means long ago. In everyday life, distance and time are separate things. A city can be 1,000 kilometers away, but it still exists now. A mountain can be visible from far across a valley, yet we are seeing it in the present. Our brains were shaped for rooms, roads, weather, faces, and horizons. They were not shaped for a universe where distance itself becomes a kind of time machine. But light takes time to travel. That is the quiet fact under everything that follows. The moon we see is not the moon of this instant. It is the moon as it was a little over a second ago. The sun is not the sun of this instant either. We see it as it was about 8 minutes earlier. Those delays are so small that daily life absorbs them without complaint. Nothing feels strange yet. Nothing feels unstable. Now scale that up. Look at a star that is hundreds of light years away, and you are seeing a message that began moving through space before your grandparents were born. Look across a galaxy, and the delay becomes so large that human history starts to feel like a surface scratch. Look beyond our galaxy, far beyond the local neighborhood of stars and dust and familiar constellations, and you're no longer observing distant things in the ordinary sense. You're watching reality in earlier states. You're catching light that set out on its journey before Earth looked anything like it does now, before mammals ruled the surface, before our planet had continents arranged in their current shapes, before the sun itself had finished much of the story we would call normal. That alone is remarkable, but it is not the part that unsettles cosmologists. The unsettling part is what Webb began finding when it looked into one of the most important stretches of all cosmic history, the first few 100 million years after the Big Bang. If you picture the age of the universe as a long human life, nearly 14 billion years compressed into a single lifespan, then Webb is peering back toward infancy, not adolescence, not maturity, infancy. The opening months, in human terms, a time when we would expect simple beginnings, uncertain structure, maybe the first fragile hints of what later becomes familiar. Instead, in some of those earliest visible epochs, Webb found systems that looked too bright to be comforting. Brightness matters. It is easy to hear that word and treat it as decoration, as if astronomers were just saying these galaxies looked pretty or intense. But brightness in this context is never just beauty. It means activity. It means stars are forming, or have formed, in large numbers. It means energy is being released. It means matter has clumped, collapsed, and started doing organized things. Brightness is evidence that work has already been done. That is the first break in intuition. We expected the early universe to resemble a landscape before dawn, with maybe a few weak lights scattered far apart. What Webb often suggested was closer to looking at a city much earlier than you thought possible, and finding not just one lamp in one window, but whole districts already glowing. Not complete cities, no, not modern skylines, but enough light, enough structure, enough evidence of fast construction to make people pause and ask whether the opening pace of cosmic history was more aggressive than we had imagined. And this is where it helps to be careful. Careful does not mean timid. It means honest enough to keep the wonder real. The strange thing is not that Webb destroyed everything scientists knew. That is the lazy version of the story, and reality is more interesting than that. The strange thing is that our broad framework still stands while some of its early chapters are being pressured from within. The universe is not refusing to make sense. It is refusing to be as simple as our cleaned-up explanations made it sound. Webb was built for this kind of seeing. Earlier telescopes changed our view of the cosmos forever, but Webb has a particular advantage for the deep past, because the universe expands. Light from extremely distant objects gets stretched on its way to us. What may have left those objects as visible or ultraviolet light arrives shifted toward the infrared. In other words, the deeper you try to look into cosmic history, the more the universe itself has moved the evidence out of the range human eyes would imagine and into a longer, redder form of light. Webb was designed to work in that territory. So when Webb stares into deep time, it is not merely using stronger glasses, it is tuned to hear a part of reality that older instruments were less able to catch. It is like searching for voices in a room after someone has changed the pitch of every sound. If you bring the wrong instrument, the room seems empty. Bring the right one, and suddenly it is crowded with whispers. That is why the first images felt so important. They were beautiful, yes, but beauty was never the real event. The real event was that those images contained a density of early information that many people had only imagined in outline. Points of light, arcs, smears, tiny structures so distant that each one was less an object in the usual sense than a document, from a time when the universe itself was still changing its basic texture. Because the early universe was not just empty space with a few stars dropped into it. It was undergoing a transition. After the Big Bang, the cosmos cooled, matter formed, atoms formed. And for a long stretch there was a kind of darkness before the first stars and galaxies began flooding space with light. Even after those first lights appeared, the universe was not yet fully transparent in the way we casually imagine today. There was a cosmic fog to its youth, a thick presence of neutral hydrogen that absorbed certain kinds of light. Over time, radiation from early stars and galaxies began ionizing that gas, clearing the fog, opening holes in it, turning a murky universe into a transparent one. This is one reason the first billion years matter so much. It is not simply the beginning because it is early. It is the beginning because that is when the cosmos is learning how to become visible to itself. And Webb stepped directly into that threshold. If you have ever driven through dense mist before sunrise, you know the feeling. At first there is only a wall, then one light appears, then another, then a shape, then a whole line of trees emerges where there seemed to be nothing. The world has not changed in an instant. Your ability to see it has. That is part of what Webb is doing for us. But the analogy only goes so far, because in this case the landscape itself was also changing while the fog was thinning. The first galaxies were not sitting still, waiting to be revealed. They were forming, colliding, feeding stars into existence, and helping transform the medium around them. So when Webb saw some of these early systems shining with surprising strength, it was not just telling us there were galaxies. We already knew that there had to be. It was telling us that some of them may have become substantial, active, and visible very quickly. Quick, in cosmic terms, means something our daily minds are terrible at feeling. 100 million years sounds enormous until you place it beside nearly 14 billion. Then it becomes less like an age and more like an opening breath. And that is where the discomfort begins to sharpen. Because if these systems were already doing serious work that early, then the first stretch of cosmic history may not have been a gentle ramp at all. It may have been something harsher, faster, and more fertile than the simplified picture most of us carry. And once you allow that possibility in, the next question arrives almost immediately. How early is early enough to make the universe feel young, and how bright is bright enough to make that youth feel strangely mature? To feel that properly, we need a scale our minds can hold for a moment. Imagine compressing the entire age of the universe into a single 80-year human life. On that scale, the first 100 million years would be measured not in decades, but in months. It would be as if we opened the story of a person's life expecting a sleeping infant and instead found a child already standing, already speaking in recognizable patterns, already rearranging the room, not fully grown, not finished, but far enough along to make you question how much happened before you thought anything substantial could have happened at all. That is why some of Webb's early findings landed with such force. The issue was never just that galaxies existed early. The issue was that some appeared luminous enough, and in some cases structured enough, to suggest rapid assembly. A bright early galaxy is not simply there. It has already converted vast clouds of gas into stars. It has already organized matter into something more than a weak blur at the edge of becoming. It has already accumulated history. And history takes time, or at least we thought it did. This is where our comfortable mental picture starts to come apart. Many people carry a quiet assumption that cosmic evolution proceeds like a calm construction project. First, a few materials arrive, then a frame appears, then over immense stretches of time the real structure slowly rises. There is truth in that picture, but it can also mislead, because nature does not always build in the patient, evenly spaced way a diagram suggests. Under the right conditions, gravity can be ruthless, gas can pour inward, star formation can surge, feedback from radiation and stellar death can complicate things. But the early universe was rich in raw material, dense in ways that later eras are not, and capable of episodes of growth that feel less like careful architecture and more like sudden weather. You can think of it this way. Suppose someone tells you a town began forming only a short time ago. You expect a few roads, maybe a scattering of houses, perhaps some exposed beams and raw foundations. Then you arrive and find lit intersections, smoke from workshops, crowded storage yards, and neighbourhoods already shaping one another. You would not conclude that the town is ancient, but you would conclude that the pace of development was far faster, or far less orderly than your first picture allowed. That is the kind of adjustment Webb has been demanding. The deeper astronomers looked, the more they had to confront an early cosmos that often seemed unusually efficient at turning potential into structure. Some of the first reports generated dramatic headlines about impossible galaxies, and some of those headlines raced ahead of the evidence. Better data, better spectroscopy, and better modelling have softened a number of the earliest, most extreme interpretations. That is important. It keeps us honest. Some objects first thought to be impossibly massive turned out to be less outrageous than feared. Some early estimates were revised. Some of the panic was noise. But the moderation of the loudest claims is not the same thing as a return to comfort. Even after the most sensational edges are trimmed away, Webb still leaves behind a young universe that looks unexpectedly busy. That is the stronger story anyway. Not a cheap collapse of all cosmology, but a durable tension. The first few 100 million years seem to contain more light, more growth, and in some cases more complexity than many pre-Webb expectations had prepared us to feel. And brightness was only the first disturbance. Because once you have a bright object at extreme distance, the next question is obvious. What is making it bright? In some cases, the answer is intense star formation. A galaxy full of young, hot stars can blaze. In other cases, there may be an active black hole at the centre, feeding on surrounding matter and releasing enormous energy as gas spirals inward. In still other cases, both may be contributing. Sorting those possibilities out is part of the work. Webb does not hand us a neat label with every distant source. It hands us better clues. This is where spectroscopy matters, though we do not need to live inside the jargon to feel why. If an image tells you that something is there, a spectrum helps tell you what it is doing. Light can carry fingerprints. Different elements leave patterns. Different processes shape emission in different ways. So the story is not built from beauty shots alone. It is built from decoding. Webb is not just photographing remote antiquity. It is interrogating it. And some of the answers have been disorienting in a different way. Not only have astronomers found early galaxies brighter than expected, in some cases, they have found evidence that certain early systems were not chemically as primitive as the average viewer might imagine. We hear early universe and tend to picture raw simplicity, hydrogen, helium, maybe the first stars just beginning to ignite, but stars are furnaces, and once stars form, they begin changing the chemical story. They fuse light elements into heavier ones, they live, die, explode, and enrich the gas around them. A chemically enriched system is a system that already has ancestry. That matters because chemistry is time made visible. If you walk into a kitchen and smell fresh bread, you know something happened before you arrived, not because you saw the flour mixed or the dough rise, but because the air itself carries evidence of a process already underway. In the same way, when astronomers find signs that some distant galaxies are not composed only of the simplest ingredients in the simplest arrangements, it suggests that cycles of star birth and death may have begun sooner, or unfolded more rapidly than old intuition wanted to allow. The universe, in other words, may have reached certain milestones quickly. Too quickly. That is where the caution comes in. Science has to resist the seduction of that phrase unless the evidence truly demands it. Sometimes the problem is not that the universe did the impossible. The problem is that our simplified estimate of what was likely turned out to be too conservative. Webb keeps pressing on exactly that distinction. It is less a machine for proving fantasy than a machine for exposing how much real physics can do when given the right early conditions. And the early conditions were not gentle. The universe was denser then. Matter was closer together. Dark matter had already begun helping sculpt the underlying gravitational framework into which ordinary matter could fall. Gas was cooling into wells. The first stars may have been very different from many that dominate later eras, perhaps larger on average, perhaps shorter-lived, perhaps capable of rapidly altering their surroundings. Once you stop imagining the first billion years as a sleepy waiting room and start imagining it as an environment full of pressure, collapse, ignition, radiation, and feedback, the mood changes. Suddenly the brightness is still surprising, but less mystical, more physical, more severe. Still, there is a line beyond which surprise turns into something else. A galaxy that looks unexpectedly active is one thing. A galaxy whose center appears to host a black hole that is already enormous relative to the surrounding system is something more troubling, because then the question is no longer only, how did stars form so fast? It becomes, how did gravity build something so concentrated, so hungry, so early? This is where the phrase different universe begins to shift from emotional reaction to structural concern, not because the laws of nature were different in a magical sense, but because the balance of processes in the young cosmos may have produced outcomes that feel out of proportion to the slower, tidier picture we inherited. If a small early galaxy contains a black hole that already seems overgrown, it is like walking into a modest house and discovering an industrial furnace in the basement, roaring at a scale the building around it hardly seems prepared to support. And once you see that possibility, the early light stops looking merely bright. It starts to look pressurized. It starts to look like evidence that the opening act of cosmic history may have been running hotter, faster, and stranger than we were ready to hear. That sense of pressure is important, because it changes how we interpret everything that follows. When we look at a distant point of light, we are not seeing a finished system frozen in time. We're catching it in the middle of something. Gas is falling inward, stars are forming and dying, radiation is pouring out, gravity is tightening its grip. In the case of galaxies with active centers, matter is spiraling toward a black hole, heating up and releasing energy as it goes. These are not calm environments. They are dynamic, unstable, constantly reshaping themselves. So when Webb finds early systems that look intense, the deeper question is not just how bright are they, but how did they get that way so quickly? To feel that question, it helps to step away from space for a moment and think in terms of growth you already understand. Imagine a savings account that starts at zero, even with steady deposits. It takes time to build something substantial. Now imagine opening the account a short time later and finding a large balance already there. You would not assume magic. You would assume that either the deposits were far larger than expected, or they began earlier than you thought, or something about the system allowed growth to accelerate in ways your original assumptions did not include. That is the position astronomers find themselves in with some of these early black holes. Black holes are not empty holes in the casual sense. They are regions where gravity has become so intense that once matter crosses a certain boundary, it cannot escape. But before matter disappears across that boundary, it often forms a swirling disk, heating up to extreme temperatures and radiating enormous amounts of energy. That process can make a black hole visible from across vast distances. In fact, some of the brightest objects in the universe are not stars at all, but the regions around actively feeding black holes. And Webb has found evidence that some of these objects were already present very early. That is not entirely unexpected. Black holes can form from the collapse of massive stars, and the early universe likely produced stars that were both massive and short-lived. So black holes should appear relatively early. The tension comes from scale. Some of the black holes inferred in these early systems appear quite large relative to the age of the universe at the time we are observing them, not impossibly large, not violating physics, but large enough to make scientists ask whether the pathways to their growth were more efficient than we assumed. There are several possibilities, and each of them carries its own implications. One idea is that black holes grew very quickly by consuming surrounding gas at high rates. If enough material falls inward and does so in a sustained way, a black hole can increase its mass significantly in a relatively short time. But there are limits to how fast this process can proceed under typical conditions, because intense radiation from the inflowing material can push back against further infall. So for rapid growth to occur, the environment must cooperate in particular ways. Another possibility is that some black holes formed not from the collapse of ordinary stars, but from the direct collapse of large clouds of gas, skipping some intermediate steps. In that case, the starting balance would already be high, making the later growth less surprising. But direct collapse is not something we can simply assume happened everywhere. It depends on conditions that may or may not have been common. There are also scenarios involving mergers, where smaller black holes combine over time, building larger ones, and there are selection effects, meaning that the objects we can most easily detect at great distances are often the most luminous and extreme, potentially biasing our picture of what was typical. None of these explanations are fantasy. All of them are grounded in real physics. But what Webb is doing is forcing those explanations to be tested under pressure. It is no longer enough to say, in a general way, that black holes can grow. The question becomes whether they can grow fast enough, often enough, under early universe conditions, to match what we are now beginning to observe. And that question does not exist in isolation, because the same early galaxies that may host these black holes are also part of a larger transformation. The universe, in its youth, was not fully transparent. Light from early stars and galaxies had to fight its way through a medium that could absorb and scatter it. Over time, as more radiation poured into space, that medium changed. Neutral hydrogen became ionized. The fog began to lift. The universe transitioned from a place where light struggled to travel freely into one where it could move much more easily across vast distances. This process is known as reionization, but we do not need the word to feel the effect. Imagine standing in a valley at night filled with thick, low-lying fog. At first, you can barely see your own hand. Then a single fire appears in the distance. It lights a small circle. Then another fire appears, and another. Each one carves out a region of visibility. Over time, the circles expand, overlap, and eventually the fog no longer dominates the scene. The landscape becomes legible. Now imagine that the fires themselves are forming while the fog is still present. They are not only revealing the landscape, they are changing it. That is the environment in which these early galaxies and black holes are operating. They are not passive lights turning on in a finished stage. They are part of the process that makes the stage visible in the first place. So when Webb detects bright, active systems at these early times, it is also providing clues about how quickly the universe was clearing its own obscuring medium. If galaxies were numerous and energetic enough, they could have played a significant role in driving this transformation. If they were rarer or weaker, the timeline would look different. Webb's data feeds directly into that question. And the answers, so far, lean toward a universe that was capable of substantial activity earlier than many simplified narratives suggested. There is a temptation, at this point, to jump to a dramatic conclusion, to say that everything we thought we knew is wrong, or that the universe behaved in ways that defy our understanding, but that leap is not necessary, and it is not accurate. What is happening is more subtle, and in many ways more interesting. Our broad picture of the universe remains intact. The expansion of space, the existence of dark matter, the formation of structure through gravitational collapse, the life cycle of stars, the emergence of galaxies, these are not being erased. Instead, Webb is tightening the constraints. It is showing us that some of the early steps in this process may have unfolded under conditions that allowed faster growth, more intense bursts of activity, or more efficient use of available material than we had fully appreciated. In other words, the rules did not change. The outcomes were more extreme. That distinction matters, because it keeps us grounded. It prevents us from drifting into the idea that we are looking at something magical or disconnected from the rest of physics. At the same time, it preserves the sense of discovery. Because if the early universe was more productive, more chaotic, and more capable of building structure quickly than we expected, then our mental model of how complexity emerges over cosmic time needs to be refined. And that refinement does not stay confined to distant galaxies. It reaches into something even more fundamental, how we measure the universe itself. Because while Webb has been revealing these early structures, it has also been used to revisit one of the most persistent puzzles in modern cosmology. A puzzle that does not live in the distant past alone, but in the way we connect the past to the present. A puzzle about how fast the universe is expanding. And the uncomfortable truth is that Webb did not make that puzzle go away. In some ways, it made it harder to ignore. That puzzle has a deceptively simple shape. If the universe is expanding, then galaxies are moving away from each other, and the farther away a galaxy is, the faster it appears to recede. This relationship is not abstract. It can be measured. You look at distant galaxies, you analyze their light, you determine how much that light has been stretched by the expansion of space, and you infer how fast the universe is growing at different distances. Over time, astronomers developed two main ways to estimate this expansion rate. One approach looks at the relatively nearby universe. It builds a ladder of distance measurements, starting with objects we understand well, like certain types of stars whose intrinsic brightness can be inferred. By comparing how bright they appear to us with how bright they should be, we estimate their distance. Then we extend that method outward, step by step, to more distant galaxies, anchoring each rung to the previous one. This gives a direct observational measurement of how fast the universe is expanding in the more recent cosmic past. The other approach looks much deeper into time. It uses the faint afterglow of the Big Bang itself, the cosmic microwave background, and models how the early universe evolved. By fitting observations to those models, scientists can infer what the expansion rate should be today, given the conditions of the early cosmos. In a perfectly tidy universe, these two methods would agree. But they do not. The expansion rate derived from nearby observations and the rate inferred from the early universe do not match. The difference is not enormous, but it is persistent. It has survived better measurements, more careful analysis, and repeated scrutiny. This is known as the Hubble tension, and it has become one of the most intriguing unresolved issues in cosmology. For a while, there was a comforting possibility. Maybe the discrepancy was due to measurement error. Maybe the distance ladder had hidden biases. Maybe the instruments needed calibration. In that scenario, new, more precise observations could bring the two estimates into alignment, restoring a sense of order. Webb was part of that test. Because if there were subtle errors in the way we were measuring distances to nearby galaxies, Webb's capabilities could help refine those measurements. It could observe key objects with greater clarity, reduce uncertainties, and potentially reveal whether the tension was simply a matter of imperfect data. But that is not what happened. When Webb's observations were brought into the picture, they did not neatly resolve the discrepancy. Instead, they supported the idea that the difference is real, not just an artifact of sloppy measurement. That does not mean we know exactly what is causing it. But it does mean that one of our most basic descriptions of the universe, how fast it expands, may be missing something. And that is where the earlier discussion comes back into focus. Because now we have two threads pulling in the same direction. On one side, Webb is showing us an early universe that appears, in some respects, more active and more efficient at building structure than many expected. On the other side, it is confirming that our understanding of cosmic expansion may not be as complete as we thought. Neither thread, on its own, breaks the story. Together, they make it harder to ignore that the opening chapters of the universe may contain subtleties we have not fully captured. This is where the phrase from the Nobel Prize winner begins to carry real weight. When someone at that level suggests that we may have misunderstood the universe, it is not a claim that everything is wrong. It is a recognition that even in a field built on precision, there are moments when new data exposes a gap between our models and reality. Not a collapse, a gap. To understand why that matters, we have to be careful with our language again. The universe is not required to behave in a way that feels intuitive. Our intuitions are shaped by human-scale experience, gravity that is weak, speeds that are slow, distances that are small, and timescales that fit within a lifetime. Cosmology operates far outside that domain. It is already remarkable that we can construct models that work as well as they do. But when those models are pushed to their limits, when we look as far back as we can, or measure with the greatest precision we can achieve, they sometimes reveal tensions, small mismatches, persistent discrepancies, patterns that suggest that our current description is close, but not final. And Webb is amplifying that process. It is not introducing chaos, it is sharpening the picture. Think about what that means for a moment. For decades, the early universe was something we understood mostly through indirect evidence and theoretical reconstruction. We had glimpses, hints, and models. Now, we have a telescope capable of directly observing objects from those early times with unprecedented detail. It is as if we have moved from reconstructing an ancient city from scattered ruins to walking its streets and noticing that some buildings are older, larger, or more intricate than we expected. You do not throw out your map when that happens, but you do revise it. And revision, in this context, is not a weakness. It is the process by which understanding becomes more precise. Still, there is a deeper emotional layer to all of this, one that is easy to miss if we focus only on data and models. We are looking at the universe in its youth. Not metaphorically, literally. The light Webb captures began its journey when the cosmos was only a small fraction of its current age. It has travelled for billions of years, across expanding space, through regions that have changed and evolved, to arrive at a mirror positioned far from Earth, shielded from heat and noise, designed to catch these ancient signals. And we can interpret them. That fact alone is extraordinary. A species that emerged on a small planet, orbiting an ordinary star, in a galaxy among billions, has built an instrument capable of reading messages from the earliest visible epochs of the universe, messages that carry information about processes that occurred long before our planet formed, long before our sun stabilized, long before anything we would recognize as familiar existed. There is a temptation to frame that in grand, almost poetic terms, to say that we are connected to the universe, or that we are the universe becoming aware of itself. But we do not need those phrases to feel what is actually happening. We are late. That is the simpler truth. The universe did not wait for us. It began, evolved, formed structure, and went through vast transformations long before we appeared. By the time Earth formed, the universe was already billions of years into its story. By the time humans began to think, it was deeper still into its development. And yet, despite arriving so late, we can still look back. We can still recover traces of the opening act. We can still see, in faint light stretched across unimaginable distances, evidence of how the first galaxies formed, how the first stars ignited, how the first structures began shaping the cosmos into something more complex. And now, with Webb, we are beginning to see that those first steps may not have been as tentative as we once imagined. They may have been bold. They may have been fast. They may have been, in certain ways, already closer to the complexity we associate with later epochs than our simplified mental picture allowed, which leads to a question that feels almost unavoidable once you sit with it long enough. If the universe was already capable of such activity so early, then what exactly do we mean when we call it young? We tend to use the word young as if it carries a clear human meaning. In our lives, young usually implies incomplete, fragile, still learning how to function. A child cannot do what an adult can. A structure just beginning cannot bear the weight of a finished one. Early stages feel tentative. But the universe does not grow like that. When we say the universe was young, we are speaking about time, not capability. The early cosmos had different conditions, not necessarily weaker ones. In some ways, it may have been more extreme, more compressed, more primed for rapid change than the vast, spread-out universe we inhabit now. Think about pressure. If you compress gas into a smaller space, it does not become quieter, it becomes more intense. Temperature rises, interactions become more frequent. Processes that might take longer in a diffuse environment can happen faster in a dense one. The early universe, compared to today, was denser. Matter was closer together. The raw ingredients for structure were not scattered across enormous distances yet. Gravity had less empty space to overcome. That changes the tempo. So when Webb shows us galaxies forming and shining earlier than expected, part of what we are seeing may be the natural consequence of a universe that began in a more crowded, more energetic state. Not a different set of rules, but a different starting configuration, one that allowed certain processes to run quickly, sometimes violently, sometimes in bursts that feel surprising, only because we are used to thinking in the calmer, later-era conditions we observe around us. Still, density alone does not answer everything. Because even in a dense environment, there are limits. There are constraints on how fast stars can form, how quickly black holes can grow, how efficiently gas can cool and collapse. Those limits are not arbitrary. They come from the physics of radiation, gravity, thermodynamics. So when Webb reveals early systems pushing against our expectations, the question is not simply, was the universe denser? It is, were the pathways to complexity more efficient than we modelled? Efficiency is a subtle word here. It does not mean perfection. It does not mean everything formed smoothly or optimally. In fact, the early universe may have been anything but smooth. Turbulent flows of gas, violent star formation, frequent mergers between small structures. These processes can create rapid growth, but they also create chaos. Efficiency, in this context, means that enough of that chaotic activity translated into stable structures quickly enough to produce what we now observe. Imagine rain falling on a landscape. If the ground is dry and the channels are shallow, water spreads slowly, meandering, pooling in small depressions. But if the terrain already has deep grooves, if the ground is shaped in certain ways, water can rush, carving paths quickly, gathering into streams and rivers faster than you would expect from a gentle drizzle. The early universe may have had its own version of those grooves. The invisible scaffolding provided by dark matter could have created gravitational wells that guided ordinary matter into certain regions. Gas falling into those wells could have cooled and formed stars more readily under the right conditions. Feedback from those stars, radiation, winds, explosions, could both disrupt and stimulate further growth. It is not a single process. It is an ecosystem of processes interacting. And Webb is showing us snapshots of that ecosystem already in motion. This is where the feeling of a different universe begins to sharpen again. Not because the physics is unfamiliar, but because the balance between processes may have been shifted. The early cosmos may have favoured rapid assembly in ways that later epochs do not. Over time, as the universe expanded, matter became more diffuse, interactions became less frequent. The pace of certain kinds of growth slowed, the environment changed. So when we look back, we're not just seeing an earlier version of now, we're seeing a different regime. That distinction matters, because it explains why our intuition struggles. We're trying to project present-day conditions backward, expecting them to scale neatly, but the universe does not scale neatly across all eras. Its behavior depends on context, on density, on temperature, on the distribution of matter, on the interplay between radiation and gravity. And when that context shifts, the outcomes shift. This brings us back to those early galaxies that seem to carry more history than expected. When astronomers analyze their light, they are not just measuring brightness. They are looking for patterns that indicate what kinds of stars are present, what elements exist, how much dust may be there, how active the system is. Each of those clues adds a piece to the puzzle. A galaxy that shows signs of chemical enrichment suggests that stars have already lived and died within it. That means time has passed, or, more precisely, that processes that take time have occurred. But if the galaxy is observed at a moment when the universe itself is still very young, then those processes must have happened quickly. Again, not impossibly, but quickly enough to demand attention. It is like hearing an echo in a canyon and realizing that the sound you're hearing has already bounced, reflected, and returned before you expected it to. The path exists, the physics allows it, but the timing feels compressed. And that compression is what Webb keeps revealing. Now consider what this does to our sense of sequence. We often imagine cosmic history as a clean progression. First darkness, then the first stars, then small galaxies, then larger ones, then complex structures, all unfolding in a steady, predictable order. There is truth in that sequence. But Webb suggests that the boundaries between these stages may be less clean than we thought. Some processes may overlap more, some may begin earlier, some may proceed in bursts rather than smooth curves. In practical terms, that means the early universe may have contained pockets of rapid development alongside regions that remained more primitive. Not a uniform field of identical beginnings, but a patchwork of environments, each evolving according to local conditions. If you were to walk through such a landscape, if that were possible, You might move from an area that feels almost untouched to one that is already active and complex within a relatively short span. The difference would not be measured in miles, but in density, in gravitational wells, in the local availability of material. Webb cannot walk through that landscape, but it can sample it. Each distant galaxy is a window into one region, one set of conditions, one outcome among many. By collecting enough of these windows, astronomers begin to see patterns, not perfect order, but statistical structure, trends that suggest how common certain behaviors were. And those trends matter. If bright, active galaxies are rare exceptions, then our models need only account for unusual cases. But if they are more common than expected, then something deeper is at play. Something about the early universe is enabling these outcomes more broadly. So the question becomes not just what is possible, but what is typical. And Webb is slowly answering that. Not all at once, not with a single image or a single discovery, but with accumulation, with repeated observations that, taken together, shift the weight of evidence. That is how science moves at this scale, not through one dramatic moment, but through a gradual tightening of understanding. Still, even gradual change can feel dramatic when it touches something fundamental. Because the early universe is not just another topic, it is the foundation of everything that came after. The structures we see today, galaxies, clusters, the large-scale web of matter, trace their origins back to those first epochs. If the early stages unfolded differently than we assumed, even in subtle ways, those differences can ripple forward through time. And that brings us to a deeper layer of the tension Webb is revealing. Not just how fast things formed, but how those early conditions connect to the universe we measure today. Because if the early universe was more active, more efficient, more chaotic in certain respects, then our models of how structure evolved over billions of years may need adjustment. And if those adjustments intersect with the way we measure cosmic expansion, then the threads begin to intertwine. You start to see that this is not a collection of separate puzzles. It is one story, seen from different angles, a story in which the opening chapters are becoming clearer, but also more complex. A story in which the data is not contradicting itself, but challenging us to refine how we connect its pieces. And once you begin to see it that way, another realization starts to form, quietly, almost in the background. We are not just discovering that the early universe was active. We are discovering that our own mental picture of simplicity at the beginning may have been too simple to begin with. That may sound like a small correction, but it changes the emotional tone of the whole story. For a long time, many of us carried an image of the beginning that was almost architectural in its neatness. First the bare framework, then the first stars, then the first small galaxies, and only much later the richer, heavier, more chemically complicated universe we know today. It was a useful sketch. It made the chronology easy to teach. It gave the mind places to stand. But sketches can become habits, and habits can harden into intuitions that reality never promised to respect. What Webb is doing, quietly and repeatedly, is reminding us that beginnings can already contain momentum. A beginning is not always a blank page. Sometimes it's a page under pressure, where the ink is already spreading faster than expected. That is especially true in a universe governed by gravity. Gravity does not wait politely. It amplifies tiny imbalances. A region with slightly more matter than its surroundings pulls in more matter. That additional matter deepens the well, making it easier to gather still more. Under the right conditions, a smaller symmetry can grow into a meaningful structure. The early universe was full of such seeds, inherited from even earlier physics, and over time those seeds became the large-scale architecture of galaxies, clusters, and the cosmic web. So when Webb shows us young galaxies that seem unexpectedly substantial, it may be telling us that some of those seeds matured with startling efficiency. Not everywhere, not uniformly, but often enough to matter. And this is where the human mind starts to lose traction, because our instincts prefer linear growth. We understand slow accumulation, one brick, then another, then another. Cosmic structure does not always behave like that. It can behave more like rainfall gathering into a floodplain. At first it seems diffuse and directionless. Then channels form, then flow concentrates. Then suddenly the landscape reorganizes around those paths. The water was always obeying gravity. The surprise comes from how quickly a loose pattern becomes a defined one. The early universe may have had that quality, a loose beginning turning into organized structure with a speed that feels abrupt when viewed from a later, calmer age. This matters especially when we talk about star formation, because stars do more than provide light. They reshape their surroundings. Massive young stars emit intense radiation. They can ionize nearby gas, push on it, heat it, and alter the conditions for further collapse. Then, when some of them die, they can explode, spreading heavier elements into the surrounding medium. Those elements change the thermal behavior of gas. They influence cooling. They influence how later generations of stars form. In other words, the first stars did not simply appear and sit there. They modified the environment. They changed the future. That is one reason chemical enrichment matters so much in the early universe. A chemically enriched galaxy is evidence not just of star formation, but of prior cycles of transformation. It suggests that the cosmos, in that region, has already been through more than one round of becoming. If you expected to find a raw construction site and instead found forged tools, ash, and repaired walls, you would understand immediately that you arrived later in the process than you thought. Some of Webb's observations create that feeling. It is worth pausing here, because this is the point where oversimplified storytelling usually makes a mistake. It jumps from earlier than expected to impossible. But earlier than expected does not mean impossible. It means expectation needs work. It means the model we held in our head was too frictionless, too averaged out, too unwilling to admit how uneven and rapid early development could be under favourable conditions. And favourable in cosmology does not mean comfortable. It means dense, unstable, and rich in consequences. Try to picture a universe where gas clouds collapse into stars more readily in some regions, because gravity has already deepened the terrain. Picture those stars turning on in bursts, pouring out ultraviolet light, shaping the gas around them, dying quickly if they are massive, and seeding the next generation with heavier elements. Picture some galaxies colliding or merging while all of this is still happening. Now picture black holes feeding within that same environment, sometimes modestly, sometimes with astonishing appetite. That is not a nursery in the soft human sense. It is a furnace floor. Suddenly the phrase young universe starts to feel less like innocence and more like compression. And compression changes everything. If the entire cosmic story was stretched across a continent, the early epoch's Webb studies would occupy only a narrow strip near the shore. Yet within that strip, some regions already show signs of intense development. That is what makes the findings feel so strange. Not merely the age, but the ratio between age and outcome. It is the mismatch between how little time seems to have passed and how much appears to have happened. That mismatch is one of the deepest emotional engines in this story, because it resonates beyond astronomy. We all know what it feels like to encounter something that seems too formed too early. A child speaking with unsettling maturity. A town that somehow already has layers of history despite being called new. A machine built so quickly that you cannot quite believe the assembly timeline. There is a quiet disturbance in such encounters. Not because growth itself is alarming, but because the timing feels compressed beyond instinct. Webb keeps giving us that feeling in cosmic form. And yet the more carefully scientists examine these early systems, the clearer it becomes that the answer may not lie in one dramatic missing piece. It may lie in several moderate ones acting together. Perhaps star formation was more efficient in some early environments. Perhaps the first stars were often massive and transformative. Perhaps gas inflow into galaxies was more vigorous than simplified models assumed. Perhaps black holes had pathways to rapid initial growth. Perhaps feedback worked in ways that sometimes accelerated later structure rather than merely suppressing it. Perhaps observational bias means we first see the most luminous and unusual objects, while a broader census gradually fills in the rest. Reality often prefers combinations. That is another reason Webb is so powerful. It is not just catching spectacular exceptions. Over time, it is building a population-level view, a census, a record of what kinds of galaxies existed, how bright they were, how common they were, and how their properties changed across cosmic time. With enough of those data points, the question shifts from could something like this happen to how often did it happen, and what does that imply about the underlying physics? There is a major emotional difference between those two questions. A single extraordinary object can feel like a curiosity. A a pattern feels like a message. And the message that seems to be emerging is that the first billion years were not a slow prelude to the real story. They were part of the real story in full intensity. Perhaps not in the fully settled form that later epochs achieve, but certainly not in the weak, hesitant way popular imagination often paints them either. Which brings us back to Reionization, because this is the background transformation that turns local surprises into a cosmic scale shift. The early universe, after the first atoms formed, was filled with neutral hydrogen gas. Light from the first luminous sources did not move through that medium as freely as it moves through today's transparent cosmos. Over time, enough energetic radiation from stars and galaxies began stripping electrons from that hydrogen, ionizing it and changing the optical character of space itself. The fog did not simply lift on its own. It was lifted by what formed inside it. That matters because it means the first galaxies were not just residents of the early universe. They were participants in making the universe visible. If you have ever watched dawn seep into a heavy valley mist, you know how gradual the revelation can be. First the faintest edge of a tree, then a fence line, then roof shapes, then suddenly the whole landscape becomes readable, though only moments earlier it felt blank. Reionization is not exactly like that, but it carries the same psychological effect. Space becomes legible in stages, visibility is built, and Webb is helping us understand who did the building. If enough early galaxies existed, and if they were active enough, then they could have played a major role in this transition. That brings the brightness puzzle and the cosmic fog puzzle into the same frame. An early universe with more luminous, more numerous, or more efficient galaxies would not only look busier, it would clear itself more effectively. So now the idea of an early cosmos different from our old intuition acquires another layer. It is not only that structures formed quickly, it is that the environment was being transformed by those structures as they formed. Growth and revelation were happening together. And once you absorb that, the next step becomes hard to avoid. Because if the young universe was already producing so much structure, so much light, and perhaps so much early black hole activity, then the story is no longer just about isolated anomalies. It starts to become a question about rhythm itself, about whether the opening tempo of cosmic history was faster, rougher, and more productive than the version we learned to imagine. And rhythm is the right word, because what Webb is changing may not be the melody of cosmology so much as the tempo at which the opening bars were played. We often imagine cosmic history as if it unfolds at one stately pace, the same calm march from simplicity to complexity across billions of years. But the universe has never promised a uniform rhythm. There are eras when change slows, and eras when it surges. There are regions where matter drifts for a long time, and regions where gravity gathers it with startling force. There are quiet outskirts and crowded intersections. When Webb looks back into the first billion years, it is increasingly finding evidence that the tempo there may have been far less leisurely than the cleaned-up version of the story suggested. That does not mean everything happened at once. It means the first movements may have been full of bursts. A bursty universe feels different from a smooth one. In a smooth universe, structure appears on schedule, step by step, in the reassuring order a textbook loves. In a bursty universe, you can have pockets where gas collapses rapidly, stars ignite in violent numbers, radiation reshapes the surrounding medium, and black holes feed hard enough to announce themselves from unimaginable distances. Then, things calm. Then, another region surges. The average story might still look gradual from far away, but locally the experience is far more dramatic. You can see this even in everyday weather. A season may be described as mild in the average, but if you live through it, what you remember are the sudden storms, the heat spikes, the nights of stillness, the sharp reversals. The average is real. It is also incomplete. The early universe may have had that same quality, broadly understandable in theory, but textured in practice by episodes intense enough to change what the average feels like. That helps explain why the term different universe resonates, even when used carefully. It captures the emotional shock of encountering a regime whose outcomes do not feel like scaled-down versions of the one around us. The first galaxies are not simply tiny modern galaxies. The first black holes are not simply weaker versions of later ones. The first luminous structures are operating in a denser, harsher, more reactive environment, one where feedback loops can bite quickly, and where the distance between seed and consequence may be shorter than our intuition expects. And this is where our own position in time matters more than we usually admit. We live in a late universe. That is easy to say and hard to feel. Everything familiar to us: stable planetary orbits, long-lived stars, chemically rich worlds, galaxies already shaped by billions of years of mergers and internal evolution, belongs to a mature epoch. Even our sun is a latecomer. Earth is later still. Human beings arrive almost absurdly late, like spectators entering a theatre after most of the performance has already happened, then trying to reconstruct the opening scenes from the glow left on the stage. Webb is giving us a way to do that reconstruction with far more honesty. But honesty brings discomfort, because the more clearly we see the beginning, the less it resembles the simplified beginning we invented for our own convenience. There is a temptation to turn that into a crisis, to say that science was wrong, that experts were blindsided, that the universe is laughing at us. But that instinct confuses revision with failure. Revision is how understanding grows under pressure. The fact that astronomers are revising expectations in the face of Webb's data is not a weakness in science. It is science working exactly as it should. Still, we should not drain the strangeness out of it. Some of these early observations really are unsettling in the best sense. They force us to ask questions that once felt comfortably theoretical. How quickly can structure emerge after the Big Bang? How early can significant star formation become common? Under what conditions can black holes become massive fast enough to matter? How patchy was the first billion years? How much early dust and chemical enrichment is compatible with the timelines we infer? How does all of that connect to the larger architecture of cosmic evolution? The important thing is that Webb is not handing us one neat answer. It is making several questions harder at once. And that cumulative pressure is more significant than any single dramatic headline. Imagine walking into a house after hearing that only one room had water damage. You prepare for a local repair, then you find damp walls in the hallway, warped boards under the stairs, a window frame that no longer fits, and a ceiling stain in another part of the building. None of it means the house is collapsing, but it does mean the original problem was connected to something broader. That is what is happening here. Bright early galaxies, large early black holes, chemical maturity, the persistence of the Hubble tension, each by itself might invite one adjustment. Together, they suggest that the opening conditions of the universe may have been more subtly demanding than our previous picture allowed. And because this is a bedtime journey, it is worth slowing down and making one idea feel real. When astronomers say they are observing a galaxy from, say, a few 100 million years after the Big Bang, they are not speaking casually. They mean that the light reaching Webb began its journey when the entire universe was younger than some mountain ranges on Earth feel to us in relation to written history. If the universe's life were compressed into a single calendar year, those observations would belong to the first days of January. Everything we know as human civilization would be less than a final breath on December 31st. That is the scale gap we are dealing with. So when Webb sees signs of mature behavior in that January light, the disturbance is easy to understand. It is like opening the first pages of a diary and finding not childish marks, but already developed handwriting, complicated thoughts, and evidence of events that seem to require pages you have not yet read. You do not assume the diary is fake. You assume the life became complex earlier than you imagined, or that the sequence in your head was too clean. That is why this story remains so compelling even after the loudest headlines are trimmed back. The deeper tension survives moderation. And moderation matters here. Some of the earliest public reactions to Webb's results moved too fast. Extreme mass estimates drew attention. Claims that standard cosmology had collapsed spread quickly. Then better analysis arrived. Spectroscopic confirmations replaced rougher photometric guesses. Models improved. Some dramatic outliers came back toward more plausible ranges. That is not embarrassing cleanup. That is the process by which a field separates signal from excitement. But after the dust settled, the basic emotional truth remained. The early universe still looked more capable than many people expected. More capable of making galaxies, more capable of growing black holes, more capable of changing its own transparency, more capable, perhaps, of exposing hidden weakness in our simplified models of expansion and early structure formation. Notice the phrasing, more capable, not magical, Not lawless, not broken, capable. There is something almost more humbling in that word than in the language of impossibility. An impossible universe would be easy to mythologize. A capable universe forces us to become more precise. It tells us that our mistake was not underestimating mystery in the poetic sense. It was underestimating what ordinary physics can accomplish under extraordinary conditions. And extraordinary conditions are exactly what the young cosmos supplied. The gas was more pristine, yet often more strategically placed. The matter distribution was rougher, but rich in potential wells. The first stars may have burned differently. The first galaxies may have built in jagged surges. The first black holes may have found pathways to growth that later epochs rarely permit so easily. This is not a separate universe. It is the same universe in a more compressed state, where cause and consequence may have stood closer together. That closeness is one of the most important feelings to preserve as we move deeper into the story, because later cosmic time can make the universe seem slow. A galaxy collision may take hundreds of millions of years. Star populations age over enormous intervals. Expansion itself feels stately when described from the vantage point of billions of years. But in the early epochs, the ratio between available time and visible outcome becomes startling. It is as if the universe, for a while, could do more with less. And once that thought settles in, the black holes at the centres of these early systems begin to look even stranger. Because if galaxies were already gathering mass quickly, black holes may not have been passive passengers within them. They may have been active participants in shaping those galaxies from the inside out, heating gas, regulating star formation in some cases, amplifying luminosity in others, and announcing their presence long before intuition thinks they should be prominent enough to matter. That possibility changes the picture from young galaxies grew fast to something more structurally unsettling. It raises the possibility that in at least some corners of cosmic dawn, the relationship between galaxies and their central black holes had already become a serious part of the story. And that is where the next layer of strangeness begins. Because once black holes stop being distant background concepts and start becoming active presences inside very young galaxies, the emotional character of the early universe changes again. Most people meet black holes first as symbols. They belong to posters, documentaries, dramatic animations. They feel like the exotic edge of astrophysics, something rare and almost theatrical. But in cosmology, especially in the early universe, the question is much less decorative. It is structural. If some black holes became large and active quickly enough, then they were not merely strange objects hiding in remote corners. They were part of the machinery by which early galaxies evolved. To feel why that matters, imagine a growing city where the power stations are being built at the same time as the neighborhoods. If those stations remain modest, the city grows one way. If some of them become enormous far earlier than expected, the city grows another way. Heat, light, distribution, timing, even the rhythm of expansion all change. A black hole at a galaxy's center is not a power station in the literal sense, but the analogy helps. An actively feeding black hole can pour energy into its surroundings, shape the movement of gas, and alter what kinds of stars can form nearby. It can become a central influence very early. That possibility is what makes some Webb observations feel so unsettling, not only because the black holes seem to have achieved substantial size quickly, but because their host galaxies can appear relatively modest by comparison. The ratio is what disturbs the mind. It is like finding a small workshop with an industrial engine installed inside it, humming at a scale that seems out of proportion to the building. The engine fits. It is real. But it changes your sense of what the building must have been going through. And this is one of the quiet revolutions Webb is forcing on us. It is not just making us ask how early galaxies formed. It is making us ask whether, in some cases, black holes and galaxies were growing together in a relationship whose early balance was different from the more settled patterns we infer in later cosmic time. Later in the universe, there are broad relationships between galaxies and the black holes at their centers. They seem to co-evolve in deep ways. The mass of the central black hole and properties of the surrounding galaxy are often linked, as if a long conversation has taken place between them across billions of years. What Webb is hinting at is that this conversation may have started earlier, faster, and more unevenly than many people expected. That does not mean the relationship was already stable. In fact, instability may be the key. A young black hole feeding in a gas-rich galaxy may go through episodes of rapid growth, The galaxy may respond, gas can be heated or driven outward, star formation can be enhanced in one region and suppressed in another. Matter can surge inward again later. The early universe may have hosted not a tidy equilibrium, but an argument, a jagged, energetic exchange between central gravity and the galaxy trying to assemble around it. If that is true, then some of the brightness Webb sees in early galaxies may not be telling only one story. It may be telling two at once. Part of the light may come from stars forming in furious numbers. Part of it may come from matter heating as it falls toward a black hole. The same object can be both a nursery and a furnace. The same early system can be building structure while also being disrupted by the energy its central engine releases. That is a more complicated picture than the old intuition allowed, but it is also a more alive one. The young universe, in this view, was not simply filling with lights. It was full of negotiations, gas against gravity, radiation against collapse, star formation against feedback, black hole feeding against the conditions that feeding itself creates. Every bright object becomes less like a static jewel and more like a weather system. And weather is the right analogy again, because weather is what human beings understand as organized instability. A storm is not chaos without rules. It is rules interacting faster than comfort. A hurricane obeys physics perfectly. That does not make it gentle. In a similar way, the early universe may have been a place where ordinary physics produced extraordinary environments because density, timing, and feedback compressed events into forms that feel violent to intuition. This is also why the phrase "same laws, different regime" matters so much. It protects us from fantasy while preserving the real shock. A different regime means the same physics can yield very different outcomes when the environment changes enough. Water can be mist, rain, ice, a river, or steam without ceasing to be water. The rules did not change. The conditions did. And in cosmology, conditions are everything. The early universe had more matter packed into smaller effective volumes. The scaffolding of dark matter was already guiding collapse. Gas inflows could be stronger. The first generations of stars may have been unusually massive. The medium around galaxies was not yet the later, more transparent, chemically rich environment we know. If you put all of that together, you get a stage on which black holes may have found chances for growth that feel rare from the vantage point of the modern cosmos. Still, we have to let uncertainty breathe where it deserves to. Astronomers do not yet possess one complete answer for how the earlier substantial black holes formed. There are competing scenarios, and that is a sign of a living field, not a confused one. Some black holes may have begun as the remnants of massive early stars and then fed aggressively. Some may have started from larger initial seeds through direct collapse of gas clouds under special conditions. Some may reflect a mixture of channels. In some cases, the most extreme-looking examples may be easier to detect than quieter ones, which means the universe first introduces itself through its loudest voices. That last point matters a great deal. Webb is an extraordinary instrument, but it does not remove selection effects from nature. If you are trying to hear faint music through a storm, the first notes you notice may be the loudest instruments. That does not mean they are the whole orchestra. It means they are the easiest to catch at first. So part of what we are experiencing may be a bias toward the conspicuous. The most luminous early systems stand out. The black holes feeding most actively are easier to identify. As Webb continues surveying more of the sky and building larger samples, the statistical picture becomes richer. Some early extremes may turn out to be less common than first impressions suggested. Others may prove surprisingly representative. This is why patience remains part of the wonder. The story is still unfolding. But even with that patience, one thing is already difficult to ignore. The opening act of cosmic history appears less timid than expected. That has consequences far beyond the emotional drama of black holes. It affects how we think about the assembly of galaxies in general. If central black holes could become influential early, then the growth of galaxies themselves may have been shaped from the inside sooner than our cleaned-up sketches implied. If early galaxies also helped drive reionization, then the same systems were not just assembling themselves, they were participating in changing the transparency of the wider universe. Now the young cosmos starts to look less like a set of isolated construction sites, and more like an interacting ecosystem. Galaxies do not merely exist within a background, they alter the background. Black holes do not merely sit inside galaxies, They influence them. Radiation does not merely illuminate space, it transforms the medium through which later light will travel. Once you begin to feel that, the early universe stops being a sequence of objects and becomes a field of consequences. A galaxy turns on and changes its surroundings. A black hole feeds and changes its host. Many such systems emerge, and together they begin to alter the optical character of the cosmos itself. Local events accumulate into global transitions. That is how a universe grows real. Not by adding pieces one by one in isolation, but by letting those pieces begin shaping each other as soon as they appear. And there is something quietly profound in realizing that we are only now, billions of years later, developing instruments good enough to watch those early negotiations take shape. We are watching the first crowded intersections of cosmic history, the places where structure, light, feedback, and opacity were all entangled. We are seeing a young universe that does not look blank, but burdened with momentum. Which is why the next question is not just how these objects formed, it is how common such intensity really was across the first billion years, and whether the universe, in its youth, was filled with far more active neighborhoods than we once dared to assume. That question matters because science changes character when a surprise stops being a curiosity and starts becoming a population. One unusual galaxy can be explained away as a rare case, a fluke of observation, an object caught in an especially dramatic moment. A handful of unusual galaxies can still be treated cautiously. But if a survey begins to reveal that certain kinds of early brightness, certain kinds of early activity, and perhaps certain kinds of early black hole growth are not isolated accidents, then the argument shifts. We are no longer asking why nature produced an exception. We are asking what kind of universe makes such exceptions easier than we expected. That is exactly where Webb becomes most powerful, not only in discovering individual extremes, but in turning deep-field glimpses into something closer to a census. A census is slower than a headline. It is also more dangerous to old intuition. Because old intuition can survive one anomaly, it struggles much more when the anomaly has neighbours. This is one of the reasons the early Webb images felt so unsettling to astronomers who had spent years modelling the first galaxies. The question was never simply whether there would be anything there. The question was how much would be there, how often, how bright, how chemically evolved, and how early. Webb began answering not with silence, but with a field crowded enough to force a different emotional posture. Instead of squinting into a nearly empty darkness, we were suddenly dealing with an early cosmos that looked populated. Not fully populated in the late universe sense, not settled, not mature in every dimension, but populated enough to change the conversation. Imagine arriving at what you were told was the edge of a newly formed frontier and finding, not wilderness broken by a few huts, but clusters of workshops, storehouses, smoke, roads beginning to define themselves, and patterns of movement already emerging. You would not say the frontier was old. You would say that frontier conditions allowed rapid organization. That distinction is everything. And here, again, we have to resist the cheap version of the story in order to reach the better one. The cheap version says the universe should have been empty, but it was full. The better version says the universe should have been relatively sparse and primitive by comparison with later times. Yet in important regions it appears to have been capable of building complexity earlier and more energetically than many simplified expectations suggested. That sounds less dramatic on paper. It is more dramatic in reality. Because it means the first billion years were not just a prelude, they were already thick with consequence. As more observations accumulate, astronomers can begin asking subtler questions. How many faint galaxies were there compared with bright ones? How quickly did the distribution of galaxy sizes change? How common were active galactic nuclei, the luminous signatures of feeding black holes? How much dust and chemical enrichment existed in different epochs? Which early systems were compact and intense, and which were more diffuse? What fraction of the ionizing radiation needed for reionization could plausibly come from these populations? Each of those questions sounds technical, but each one points towards something deeply intuitive. They are all asking, in different ways, what kind of place the young universe really was. Was it mostly dark with rare sparks? Was it patchy but vigorous? Was it already crowded with small but efficient builders? Did a relatively modest number of bright systems do most of the work? Or was the deeper truth that the early cosmos contained a hidden abundance of less dramatic galaxies, each contributing a little, together changing everything? Webb is helping separate those possibilities. And as it does, the image of the early universe becomes less like a silent vacuum waiting for history and more like a landscape where history arrived quickly in uneven waves. That patchiness is especially important. We often speak about the early universe as if it were one uniform state, but no interesting place is ever experienced uniformly. Even on Earth, dawn does not arrive identically everywhere. Fog burns off at different rates. Cities wake sooner than fields. Mountains catch light before valleys do. The first billion years of cosmic history may have had a similar patchwork character. Some regions lit up quickly. Some remained darker longer. Some became efficient engines of star formation. Others lagged behind. If that is true, then the phrase different universe carries yet another meaning. It was not only a different regime in time, it was a more uneven one than our averaged-out diagrams encouraged us to imagine. Averaging is useful. It is also emotionally deceptive. Average conditions can hide the lived reality of extremes. A coast may have a mild average climate while still experiencing violent storms. A city may have moderate average traffic while still producing daily bottlenecks that define how it actually feels to move through it. The early universe may have been moderate in some overall parameters while still producing local environments that were ferociously efficient at building structure. Webb is particularly good at bringing those local environments into view, because it is sensitive to the light from the very galaxies most involved in these transitions. Not every early object is equally easy to detect, and that fact should keep us honest. But the pattern emerging is already hard to dismiss. Cosmic dawn was not emotionally blank. This also changes how we think about the first stars. For many years, the first stars existed partly as theory and partly as consequence. We knew they must have formed. We knew they must have influenced later structure. But directly observing individual first-generation stars is extraordinarily difficult. Instead, we infer their presence through what they leave behind: ionization, chemical enrichment, later stellar populations, the behavior of early galaxies. Webb's observations of early luminous systems help tighten those inferences. They make the first stellar generations feel less like abstract prerequisites and more like active participants in a crowded opening chapter. And once you start seeing those first generations as active participants, time itself begins to feel different. 100 million years still sounds immense on human terms. It is beyond any civilization, beyond all recorded history, beyond the rise and fall of species. Yet on cosmic terms, especially in the context of what Webb is observing, it can begin to feel startlingly brief. Brief enough for the first major structures to emerge, brief enough for stars to live and die, brief enough, perhaps, for black holes to begin asserting themselves, brief enough for some regions of the universe to start changing the transparency of space around them. That is hard for the mind to hold, not because the numbers are large, but because the ratios are strange. So much consequence packed into such a small slice of the total story. This is where I think the emotional centre of Webb's discoveries really lives. Not in the most sensational objects taken one by one, but in the compression of becoming. We are watching a universe in which becoming happened fast enough to disturb us. You can hear that as bad news for our models if you want. I think it is better heard as a correction to our sense of what beginnings are allowed to be. We wanted a long, simple runway before complexity. Nature may have preferred a shorter, harsher takeoff. And that takeoff matters for everything that came later. Because the galaxies that form early influence the later merger history of larger systems. The black holes that start feeding early can become seeds for the monstrous black holes found in mature galaxies. The radiation that helps clear neutral hydrogen changes what later light can do. The first enrichments in heavy elements alter the chemistry from which later stars, planets, and eventually living worlds emerge. In that sense, the early universe is not merely the beginning in chronological order. It is the stage where the conditions of later possibility are being laid down under pressure. So when Webb shows us an early cosmos rich with active neighbourhoods, it is showing us more than a set of exotic objects. It is showing us the opening negotiations that made later history possible. And the most unsettling part may be that this opening act still does not fully reconcile with our measurements of the larger universe. Because while Webb is deepening our view of early structure, the tension over cosmic expansion remains. The same instrument that is revealing a busier than expected youth is also helping confirm that the universe, when measured by different methods, continues to tell us slightly different stories about how fast it is growing. At some point, those stories stop feeling separate. They begin to feel like different edges of the same unresolved picture. That unresolved picture is what gives the whole Webb era its unusual emotional force. If all we had were the early galaxies, we might say the universe was simply more efficient at building structure than expected. If all we had were the expansion rate discrepancy, we might say there is probably some hidden systematic error, or some modest adjustment still waiting to be made. But when both threads remain alive at the same time, the feeling changes. The young universe appears more active than many of us imagined, and the mature universe still refuses to yield a fully unified answer about how fast it expands. The result is not confusion, it is pressure. Pressure on the seams of the story. And seams are where revision begins. The Hubble tension sounds abstract until you realize what it implies. One way of reading the universe, using the nearby cosmos and careful distance measurements, gives one expansion rate. Another way, using the ancient afterglow of the early universe and a model of how everything evolved forward, gives another. These values are close enough to describe the same reality, but far enough apart to resist easy dismissal. It is like hearing the same melody played by two different instruments and noticing that one is consistently sharp. Not enough to become a different song, enough to tell you that something in the tuning is off. For a while, it was reasonable to hope that better measurements would make the discrepancy shrink. That hope was not naive, it was disciplined. Science often resolves tension by discovering that one of the measuring tools had a subtle flaw. But Webb's contribution here has been sobering. By re-examining key steps in the local distance ladder with its own precision, it did not erase the mismatch. It strengthened the case that the mismatch is real enough to take seriously. That matters because the tension lives at the junction between early and late cosmic history. In simple terms, one story of the universe begins from the young cosmos and calculates forward. The other begins from the more recent universe and measures outward. If both are correct and complete, they should meet cleanly. The fact that they still do not means either that one side has hidden complications we have not fully isolated, or that the model connecting early and late times is missing some ingredient. Now place that alongside Webb's view of the first galaxies. The same broad era that should, in a simplified account, look relatively raw is instead offering signs of unexpected rapidity. The same cosmological framework that works astonishingly well at many scales is encountering stubborn edge cases where the details resist neat closure. None of this proves a dramatic overthrow, but it does create a mood that serious scientists recognize immediately. The feeling that the universe is not done teaching you how to describe it. And perhaps that is what made the different universe warning resonate so widely. It was not because the phrase was flashy, it was because it captured a genuine shift in posture. The early universe, as Webb reveals it, is not merely distant. It has a different texture from the one many people were carrying in their heads, a different tempo, a different balance between darkness and light, between infancy and intensity, between local structures and the global environment those structures were changing. You can feel that difference most clearly if you return, for a moment, to the idea of transparency. Today, space feels visually open to us. We look out, and aside from dust and local obstructions, light can travel huge distances. That is part of why astronomy exists at all. But the early universe did not begin in that condition. It had to become transparent in the relevant sense. It had to pass through a long transformation as early luminous sources ionize the surrounding hydrogen and change the optical character of the cosmos. So the same galaxies Webb is finding are not just signs that structure existed. They are clues to how the universe made itself more see-through. That means the young cosmos was not only making objects, it was altering the stage on which later observation becomes possible. There is something deeply unsettling and beautiful about that. The early lights did not simply appear inside darkness. They fought with it. They carved visibility into it. They were participants in changing the conditions of cosmic legibility. A later universe like ours, where light can travel so freely, is in part the descendant of those first successful assaults on opacity. If you picture that physically, the whole story becomes easier to feel. Think of a valley before dawn, full of heavy fog. Then imagine scattered fires being lit across the landscape. At first, each fire creates only a small circle, but the circles grow. More fires appear. Their zones of clarity overlap. The valley does not become clear everywhere at once. Instead, visibility spreads region by region until the landscape is no longer ruled by mist. That is roughly the emotional shape of reionization. Not a single switch, a patchwork victory. And Webb is telling us that the fires may have been more numerous, or more energetic, or more efficient in some regions than many people had expected. That possibility alone makes the young universe feel less passive, but combine it with the black hole story and the expansion rate story, and the early cosmos starts to look not merely younger, but more structurally demanding. We thought we were looking back at a nursery. In some places, we may have been looking back at an industrial district already under strain. Not finished and not peaceful, but working. It is important here to keep one foot planted in restraint, because the internet is always hungry for a simple ending. Either cosmology is intact, or it is broken. Either Webb confirmed everything, or it shattered everything. Reality is less obedient than those choices. Webb is doing something more interesting than offering a verdict. It is revealing where our older confidence was too smooth. Some of the first alarming claims have already been revised. Some objects that seemed impossibly massive now look less extreme after better measurements. Some apparent tensions may narrow as datasets improve. Some of the most dramatic interpretations will probably continue to soften. This is not a retreat, it is refinement. But refinement cuts both ways. It can lower some peaks while making the broader terrain harder to ignore. And the broader terrain still suggests a universe whose opening billion years were unusually fertile. Galaxies appeared, multiplied, and in some cases blazed. Black holes likely found ways to become visible early. Radiation from early populations helped rework the transparency of the cosmos. Meanwhile, our best measurements of expansion still do not fall into the clean agreement many hoped for. The picture is not one of collapse, it is one of accumulated insistence. Nature keeps pressing on the points where our simplified story was most comfortable. For a human being, that is a strange kind of gift. We like closure because it lets the mind rest. But discovery does not always arrive as closure. Sometimes it arrives as a better form of unrest, an unrest that is more precise than ignorance and more honest than premature certainty. Webb has given cosmology a great deal of that kind of unrest. It has deepened confidence in some areas and sharpened discomfort in others. It has turned vague theoretical zones into observed territory, and observed territory has a way of refusing the elegance of the sketch that came before it. This is why the telescope matters so much emotionally, not just scientifically. It is forcing abstraction to become visual. For decades, early cosmic history lived partly in equations, partly in indirect traces, partly in imagination. Now we have direct windows into those eras. The windows are still narrow, still difficult to interpret, still mediated by immense distances and subtle analysis, but they are windows nonetheless. And once you have a window, you stop being satisfied with murals. The first galaxies are no longer only inferred, the early black holes are no longer only theoretical necessities. The transition from opacity to transparency is no longer only a clean chapter in a textbook. The mismatch in cosmic expansion is no longer easy to file away as likely error. Everything is becoming more concrete at once, and concrete reality is always stranger than the summary version, which raises a deeper possibility, one that feels almost inevitable once enough of these threads are held together. Perhaps what Webb is really revealing is not a broken universe, but one whose earliest successful structures emerged in a kind of compressed overdrive, where gas, gravity, radiation, and black hole growth were interacting in ways that made the first visible epochs feel less like the opening of a story and more like a story already accelerating. Acceleration is the word that begins to tie everything together. Not acceleration in the sense of something moving faster through space, but acceleration in the sense of development, a universe that, in its earliest visible moments, seems to have been doing a great deal in a relatively short span of time, building stars, assembling galaxies, growing black holes, changing its own transparency, establishing the conditions that later cosmic history would inherit. And once you start to see that early acceleration, the discomfort becomes more specific. Because the models we use to describe the universe are not arbitrary stories. They are built to connect one epoch to another. They take what we observe in the early universe and project forward. They take what we measure in the nearby universe and project backward. They are bridges, and a bridge depends not only on how strong each end is, but on how cleanly they meet in the middle. If the early universe was more active than expected, and if the present-day expansion rate still refuses to align perfectly with predictions, then the bridge is under tension, not collapsing, not broken, but under tension. And tension in a scientific model is not a failure, it is a signal. It tells you where to look more carefully. It tells you which assumptions were doing more work than you realized. It tells you which parts of your understanding are robust, and which parts are approximations that worked well enough until the data became too precise to ignore their limits. This is why serious scientists do not panic when they hear phrases like misunderstood the universe. They pay attention, because misunderstanding in this context rarely means being completely wrong. It means that a model that once captured reality within acceptable error is now being asked to operate outside the range where its simplifications remain invisible. Webb is expanding that range. It is pushing observation deeper into time, forcing our models to remain coherent across a wider span of conditions. And that is difficult, because the early universe is not just a scaled-down version of the present. It is a different environment, a denser, more reactive, more compressed regime where processes that feel rare or slow today may have been common and rapid. So the question becomes sharper. What, exactly, needs to change in our understanding to accommodate what Webb is showing us? Not in a dramatic, all-or-nothing way, but in a precise, disciplined way. Is it the efficiency of star formation in early galaxies? Is it the typical mass distribution of the first stars? Is it the rate at which gas can cool and collapse under early conditions? Is it the pathways by which black holes acquire their initial mass? Is it the interaction between radiation and matter during reionization? Is it something in the cosmological model that connects early conditions to present-day expansion? Or is it, more subtly, a combination of several small adjustments that together produce the larger effect? Reality often prefers that last answer. And that is why this moment in cosmology feels less like a crisis and more like a tightening spiral. Each new observation constrains the possibilities. Each improved measurement reduces the space where easy explanations can hide. The picture becomes sharper, but also less forgiving of oversimplification. At the same time, there is a human layer to all of this that is easy to overlook if we focus only on the equations behind the scenes. We are trying to understand events that happened billions of years before anything familiar existed. We are reconstructing a history that no one witnessed. We are doing it from a single location, on a single planet, orbiting a single star, in a galaxy that is not even special in the grand inventory of the universe. And yet, with instruments like Webb, we are able to gather enough information to say something meaningful about the first few 100 million years after the beginning. That fact alone should slow us down, because it changes how we relate to the story. We are not outside it. We are late participants, looking backward. And the further back we look, the more we realize that the beginning was not a quiet prologue. It was already full of consequence. There is a moment, when you really sit with that, where the ordinary night sky stops feeling passive. The stars you see overhead are not just points of light scattered randomly. They are part of a structure that traces back through layers of history, through mergers, through star formation, through chemical enrichment, through the early galaxies Webb is now revealing, all the way back to those compressed, intense first epochs. Everything familiar to us is downstream of that early acceleration. The iron in your blood, the oxygen you breathe, the silicon in the ground beneath you, the existence of stable stars like the Sun, the formation of planets, the emergence of chemistry complex enough for life. All of it depends on a universe that was capable of doing a great deal, very early on. That is the quiet meaning behind the data. Not that the universe is stranger than we imagined in some abstract sense, but that it was already productive, already inventive, already setting the stage for everything that would follow long before any observer existed to notice. And Webb is letting us notice. It is letting us see that the beginning was not just a starting point. It was an environment in which processes we now take for granted were already unfolding under conditions that made them feel compressed, intense, and in some ways out of proportion to their age. That realization does something subtle to the way we think about time. We're used to thinking of time as something that simply accumulates. More time means more development. Less time means less development. But the early universe challenges that instinct. It suggests that under the right conditions, development can happen quickly enough to blur that simple relationship, not infinitely fast, not without constraint, but fast enough that young does not automatically mean simple. And that is a difficult idea to internalize, because it asks us to let go of a comforting alignment between age and complexity. It asks us to accept that the universe, in its youth, may have already been experimenting with forms of structure that feel closer to maturity than we expected. It asks us to recognize that our intuition about beginnings is shaped by human experience, not by cosmic reality. And once you accept that, the phrase different universe begins to settle into something quieter and more precise. Not a different set of laws, not a separate reality, but a different phase of the same universe, where the balance of processes produced outcomes that feel unfamiliar from the vantage point of our late, expanded, more stable epoch. A universe where the distance between cause and consequence may have been shorter, where density amplified interaction, where feedback loops could assert themselves quickly, where light was both a product and a tool of transformation, where black holes may have stepped into prominence earlier than expected, where galaxies were not waiting politely to grow, but often surging into being. And that phase is not gone. It is still visible, not around us, but behind us, carried in the light that has been travelling for billions of years to reach our instruments. That is what Webb is collecting. Ancient momentum. And the more of it we gather, the clearer it becomes that the opening act of the universe was not simply the beginning of a story we already understand. It was the beginning of a story that is still teaching us how to read it. And learning how to read it may be the deepest theme in this entire journey. Because the universe does not hand us its history in order. It does not preserve neat labels. It does not tell us, in plain language, which brightness belongs to star formation, which belongs to a feeding black hole, which chemical signature marks one generation of stars rather than another, or which discrepancy in expansion points toward new physics rather than a hidden complication in measurement. Instead, it leaves traces, stretched light, faint patterns, ratios, spectra, statistical populations. It gives us fragments and asks whether our patience is equal to their meaning. Webb has made those fragments richer. It has not made them simple. That is why this period in astronomy feels so alive. We are not merely filling in missing details inside a finished frame. We are testing how good the frame really was. We are asking whether the opening conditions of the cosmos allowed certain pathways to structure more readily than our old intuitions admitted. We are asking whether black holes entered the story as supporting actors and later became central, or whether in some early environments they were important almost from the start. We are asking whether the first galaxies were fewer and rarer than the initial Webb fields made them seem, or whether the busyness we're seeing is telling us something durable about cosmic dawn. And we're asking all of that while the expansion rate tension continues to sit there, patient and unresolved, like a note in a piece of music that never quite resolves to the chord the ear expects. That unresolved note matters because it keeps the whole story from becoming too comfortable. It reminds us that cosmology is not only about the beauty of distant images, it is about connection. The early universe must connect to the later one. The opening conditions must flow into the mature cosmos we inhabit. A model that explains the first light but not the present expansion is incomplete. A model that explains the present expansion but underestimates the complexity of the first visible structures is incomplete too. So there is a sense in which Webb is forcing unity on us. It is making it harder to keep different cosmic puzzles in separate drawers. The first galaxies matter to the later universe. The later universe reflects the outcome of the first billion years. The transparency of space was shaped by early luminous sources. The growth of black holes fed back into galaxy formation. The rate of expansion affects how structures grow and how light travels. Nothing in this story stays politely isolated. And that is one reason the phrase different universe can sound exaggerated and still point towards something real. The early cosmos was not just different in appearance. It may have been different in how tightly coupled its major processes were. In a denser, younger universe, local events could have larger downstream consequences more quickly. A burst of star formation was not just local brightness. It was radiation entering a still-changing medium. A feeding black hole was not just a strange object, it was a pressure source inside a galaxy still assembling itself. A cluster of early galaxies was not just an observational curiosity, it was part of the machinery by which the universe altered its own visibility. If you think about it long enough, the early universe starts to feel less like childhood and more like weather at the formation of a continent. Violent rivers, rapid erosion, channels deciding where later stability will eventually settle. The land is not finished, but it is already determining what kinds of valleys and coastlines can exist much later. That is a more faithful kind of wonder than the usual cosmic clichés. It does not ask us to be impressed by size alone. It asks us to be impressed by consequence. 100 million years in the early universe is not impressive because the number is large. It is impressive because so much could happen within it. A distant galaxy is not impressive because it is far away. It is impressive because it carries evidence that structure was already under pressure there. An early black hole is not impressive because black holes are exotic. It is impressive because it may reveal how quickly central engines could become relevant inside young galaxies. The Hubble tension is not impressive because disagreement is dramatic. It is impressive because even tiny disagreements matter when they concern the total behavior of the universe. And this is where the human role comes back into focus in a calmer, more intimate way. We are creatures of local scales. We know what it means for rain to begin, for a city to wake, for iron to rust, for a child to grow, for a lifetime to pass. We do not naturally know what it means for a universe to become transparent, for galaxies to emerge from density fluctuations, or for black holes to grow inside systems younger than our instincts can properly imagine. Those meanings have to be built. They have to be translated into something our minds can hold without reducing them to cartoons. That is what good astronomy does at its best. It does not just collect data, it teaches perception. Webb is teaching us a new perception of the beginning. It is teaching us that early is not the same as empty, that young is not the same as simple, that distant is not merely far away, but deeply old, that the first visible epochs were not a vague murmur before the real story, but an active interval in which the universe was already engineering its future. This kind of seeing changes the emotional weight of the night sky, not dramatically, not all at once, but quietly. A person can go outside after hearing all of this and look up at what seems like a calm field of stars, yet hidden behind that calm is a history now made less innocent by what Webb has revealed. Somewhere in that darkness are the descendants of galaxies that formed in haste. Somewhere in that darkness are black holes that may have begun asserting themselves before intuition allows. Somewhere in that darkness is the outcome of a universe that, in its youth, may have built faster, lit sooner, and transformed itself more aggressively than we once pictured. The ordinary becomes less ordinary when you know what had to happen for it to exist. Even our own planet belongs to that chain of compression. Earth did not arise in the first billion years. It is a late world, built from material processed through long generations of stars. The atoms that make rocky planets, oceans, air, and living tissue were not available in the beginning in the forms we depend on now. They had to be forged, scattered, recycled, assembled, which means that when Webb reveals an early cosmos already moving with surprising speed, it is showing us not only the birth of remote structures, but the distant prerequisites of our own existence. Not us specifically, not human beings waiting in the design. That would be too sentimental, and it would miss the harder beauty of the truth. The truth is that a universe capable of becoming chemically rich had to begin somewhere. A universe capable of making later stars and later planets had to pass through these compressed early acts of formation, ignition, enrichment, and transformation. Webb is letting us look at those acts more directly than ever before. And directness changes responsibility. Once we can see more clearly, we can no longer pretend the sketch was enough. This is especially true for the way we talk about uncertainty. Real uncertainty is not a hole in knowledge where anything can be poured. Real uncertainty has shape, it has boundaries, it has better and worse possibilities. The fact that astronomers do not yet know exactly how every early black hole reached its observed state does not mean all explanations are equally likely. The fact that the expansion rate tension remains unresolved does not mean every speculative theory deserves equal attention. The fact that some early galaxy claims have been moderated does not mean the entire Webb anomaly landscape evaporated. Uncertainty is part of the architecture of serious seeing. It keeps wonder disciplined. And disciplined wonder is exactly the tone this subject deserves, not because the universe is fragile, but because our relationship to truth is, if we rush, we turn everything into slogans. If we flatten, we turn discovery into trivia. If we exaggerate, we lose the right to be trusted when reality is already strange enough. The better response is slower, to let the evidence accumulate, to let the image sharpen, to allow ourselves the discomfort of learning that the early universe was neither a blank simplicity nor a fantasy realm, but something harder to summarize, a real physical regime in which ordinary laws, under extraordinary conditions, produced an opening act dense with momentum. And the more clearly that momentum comes into view, the more the final question begins to change shape. It is no longer only, what did Webb find? It becomes, what kind of universe begins this way? And what does that force us to understand differently about everything that came after? A universe that begins this way is a universe that does not waste its early opportunities. That may be the clearest way to say it. The young cosmos was not sitting in silence, waiting politely for complexity to arrive later. In at least some regions, complexity was already organizing itself out of raw conditions with startling urgency. Matter was falling inward, gas was cooling, stars were igniting, radiation was reshaping the medium around those stars. Black holes were beginning, in some cases, to claim a role large enough to be visible across impossible spans of time, and all of it was unfolding inside a universe still in the process of becoming transparent to its own light. There is something deeply clarifying in that image. The beginning was not a blank stage, it was a stage under construction while the first actors were already performing. That helps explain why Webb's findings feel so different from ordinary updates in astronomy. This is not a story about adding a few new facts to a stable picture. It is a story about replacing a simplified emotional model with a more physically honest one. We thought the first visible epochs would feel quiet compared with what came later. Instead, they often feel compressed, loaded, and already full of consequence. Not everywhere, not uniformly, but enough to matter. And the phrase, enough to matter, is doing important work here, because it prevents us from drifting into theatrical extremes. Cosmology does not need theatrical extremes. It needs scale, patience, and the courage to let moderate revisions accumulate until they become undeniable. That is how a field changes, not always through a single catastrophic contradiction, but through repeated encounters with reality that keep pointing in the same direction. A little more brightness than expected, a little more early assembly than expected, a little more chemical maturity than expected in some systems, a little more black hole significance than expected, a little less comfort that the expansion tension will dissolve into measurement error. Each by itself can be managed. Together they begin to change the air. And sometimes that is how truth first arrives, not as a shout, but as a pressure change. You may have felt this in ordinary life. You walk into a room and sense that something is different before you know what it is. The furniture has shifted, or the weather outside has altered the light, or someone has opened a window. The room is still the room, but the atmosphere is not what it was. That is the Webb effect on early cosmology. The universe is still the universe. The broad structure of the story remains, but the atmosphere of the opening chapters has changed. It feels denser now, more active, less innocent. And that change in atmosphere does something valuable to our sense of ourselves. It reminds us that human intuition is a late product of a mature universe. We are adapted to a cosmos where stars already exist in abundance, where heavy elements are common enough to build planets, where the large-scale structure has had billions of years to settle into recognizable forms. We are not adapted to think naturally in terms of cosmic dawn. We need instruments for that. We need mathematics. We need disciplined imagination. Webb is one of the finest instruments of disciplined imagination we have ever built. It is easy to focus on its engineering, and rightly so, the mirror, the shielding, the orbit, the sensitivity, the years of planning. But the deeper achievement is perceptual. We built a machine capable of correcting for the limits of our minds, a machine that can collect ancient infrared light our eyes were never meant to see, and convert it into evidence we can reason about. In that sense, Webb is not just a telescope, it is a prosthetic for human comprehension. And what it is helping us comprehend is not merely distance, it is tempo. That is why the title promise really matters here. It's a different universe works best when we hear it not as a claim of magic, but as a recognition of regime change. The early cosmos was the same reality under different conditions, and those conditions altered the pace and texture of becoming. In that younger state, the ratio between available time and achieved structure appears strange to us. Strange enough to force revision. Strange enough to justify a serious scientist sounding almost unsettled in public. Because to misunderstand the universe is not always to misunderstand its laws. Sometimes it is to misunderstand its appetite. The young universe may simply have been more eager than we imagined, more able to take a dense beginning and turn it into visible structure quickly, more willing to let gravity, radiation, chemistry, and black hole growth begin entangling themselves in earnest while the cosmos was still within its first fraction of a billion years. That is the kind of realization that quietly changes later questions too. For example, if the first billion years contained more active galaxies than expected, how does that alter our picture of the build-up to later galaxy populations? If black holes found roots to early significance, what does that imply about the monsters we see at the centers of mature galaxies billions of years later? If reionization was driven by more abundant or more efficient luminous sources, what does that say about how patchy or rapid the clearing of cosmic fog really was? If the Hubble tension persists, are we missing some small but crucial ingredient in how we connect the primordial universe to the recent one? Each question leans into the next. And the reason that matters for a long-form story like this is that the reality itself is seamless. We tend to separate astronomy into topics because our minds need handles. Galaxies go in one chapter, black holes in another, cosmological expansion in another, Reionization in another. But the universe did not separate them that way. In the early epochs Webb is observing, these processes overlap, they interfere, they amplify, they constrain one another. A bright young galaxy is not just a galaxy, it is a site of star formation, a source of radiation, a clue to chemical history, possibly a host for a feeding black hole, a participant in changing the transparency of intergalactic space, a data point in the broader story of how the universe became what it is now. Once you absorb that, each object begins to feel heavier, not visually heavier, but historically heavier. A faint smudge on a detector becomes a crowded archive of processes, and that is one of the most moving things Webb has done. It has made distant objects feel historically dense, not because they are close to us emotionally in the ordinary sense, but because they are carrying so much of the world to come inside them. They are not just old, they are formative. The first billion years, viewed this way, begin to resemble the root system of a forest. Most of what later rises into view depends on what happened there, underground, out of sight, before the visible canopy ever made sense. You cannot understand the mature forest only by staring at the leaves. You have to know something about the early, hidden work of growth. Webb is giving us glimpses of that hidden work. And what it is revealing is not a tidy nursery bed, it is a root system already spreading faster than expected. There is a kind of humility that comes with recognizing that. Not the theatrical humility of saying we know nothing, but the quieter humility of discovering that our best simplified picture was too clean. We knew the broad outline. We did not yet feel the texture. Webb is giving us texture. Texture in the form of early brightness. Texture in the form of patchy emergence. Texture in the form of black hole growth that may begin influencing galaxies sooner than expected. Texture in the form of unresolved expansion. Texture in the form of a first visible universe that appears less like a whisper and more like a field of signals already competing for dominance. And because this is a story about extreme reality, it is worth saying plainly, texture is often where reality becomes most extreme, not in the largest number or the most dramatic image, but in the stubborn refusal of the real world to behave like a smooth diagram. The early universe was not a smooth diagram. It was an active environment where several forms of becoming may have overlapped in compressed, uneven, and highly consequential ways, which leaves us with one final movement to make before the story can come to rest. If Webb has shown us that the universe's youth was more productive, more entangled, and more physically intense than we were prepared to feel, then the real payoff is not only scientific, it is perceptual. It changes what it means to stand under a calm modern sky and know that hidden inside that calm is a past that was anything but calm. And once that perception changes, The ordinary night can never become entirely ordinary again. Because once you know that, the sky begins to carry two realities at once. The first is the one we live with every day, a quiet ceiling of stars, constellations that look stable enough to feel almost decorative, darkness between points of light, a sense of calm distance. The second reality is harder to feel at first, but once it enters, it stays. Hidden inside that calm is an origin story that was not calm at all. The visible piece of the late universe was built on an early period of compression, ignition, feedback, and rapid structural ambition. The stillness above us is not evidence that reality was always gentle. It is evidence that violence can mature into order. That may be one of the deepest things Webb has made easier to feel. Not that the universe is dramatic in the cheap sense, but that serenity can be late, stability can be earned. A mature cosmos can look spacious and patient precisely because so much happened before it reached this form. We are living in the afterglow of successful early complexity. Long after the first stars burned, long after the first galaxies began to organize themselves, long after the first black holes found their foothold, long after the fog of neutral hydrogen was forced to give way, we arrive and look up at the result. And because we arrive so late, we mistake the result for the process. That is the illusion Webb keeps undoing. It shows us that the early universe was not simply an emptier version of now. It was a more compressed environment with its own behavior, its own pace, its own ratios between time and outcome. A young cosmos in which cause and consequence often stood nearer together. A cosmos in which a few 100 million years could contain enough star formation, enough chemical change, enough gravitational organization, enough radiative pressure, enough black hole growth, to leave us staring at the data and quietly revising the emotional meaning of the word beginning. That revision is not a small thing. Human beings live by beginnings. We begin days, relationships, projects, civilizations. We bring to all of them a set of assumptions about what beginnings feel like. Slow, uncertain, underformed. But the universe does not care about those assumptions. Under the right conditions, beginnings can be fierce. They can be dense with consequence. They can already contain the seeds of the later order in configurations far more active than our instincts are comfortable with. The first billion years appear to have been like that. And there is something almost intimate in the fact that we can now tell. We can tell not because the universe bent itself toward our understanding, but because we became patient enough, technically skilled enough, and humble enough to build an instrument that could catch what had always been there. Ancient light crossed billions of years without knowing it would ever be read. Yet here it is, landing on gold-coated mirrors and exquisitely cold detectors, yielding patterns that a late species on a small planet can turn into a story about the opening act of everything. That does not make us central. But it does make us witnesses. And witness is a beautiful role. It is quieter than dominance, but more honest. We did not make the first galaxies. We did not ignite the first stars. We did not clear the cosmic fog. We did not feed the first black holes. We came later, impossibly later, and still found a way to look back. There is dignity in that. Not cosmic importance in the sentimental sense, but dignity in participation. We belong to a universe capable of producing observers after billions of years, and those observers are capable of recovering evidence from the deep past with enough care to feel corrected by it. That correction is part of the gift, because correction is how reality becomes more real. A simpler version of this story would have been easier to tell. It would have said the early universe was dim and primitive, then slowly became rich and structured over unimaginable time. It would have been comforting, mostly true in the broadest outline, and emotionally incomplete. Webb has not erased the outline. It has given the outline weight. It has shown us that the first visible epochs already had weather in them, already had local intensities, already had regions where the universe seems to have discovered, very quickly, how to build. That is why the phrase different universe lingers. Not because it is literally another cosmos behind a curtain, but because the universe in its youth behaved in ways that are difficult to feel from inside our mature, expanded, chemically rich present. We live among the long consequences. Webb lets us glimpse the short causes, and the short causes are sharper than expected. Sharper in their brightness, sharper in their pace, sharper in the scale of black hole growth they may allow, sharper in the role early galaxies may have played in making the universe transparent, sharper in the way they refuse to sit neatly beside every older expectation. Even the unresolved tensions matter emotionally here. In fact, they matter especially. A fully solved story would be cleaner, but perhaps less alive. The persistence of the expansion rate puzzle reminds us that cosmology has not finished converging on its own deepest picture. The moderation of some early dramatic claims reminds us not to mistake excitement for truth, and the survival of genuine pressure after that moderation reminds us that truth does not need exaggeration to be astonishing. That balance is rare. It is what makes this moment in astronomy feel so human. We are uncertain, but not lost, surprised, but not unmoored, corrected, but not humiliated, moved, but still disciplined. That is a wonderful place to be when facing something larger than yourself. And perhaps that is the final transformation Webb is making in the listener too. It is not only changing our image of the early universe, it is changing our posture toward knowledge. It invites a calmer kind of awe, one that does not depend on slogans or declarations that everything has changed forever. Instead, it asks for something harder and better. Stay with the evidence. Let your intuition be retrained. Allow the universe to become more textured than the version you inherited. Once you do that, ordinary scale begins to loosen. A century no longer feels long in the same way. A civilization becomes a very brief local event. Even Earth's deep history becomes a late chapter. The Sun becomes one more mature star in a universe that had already spent billions of years experimenting before it arrived. Our species becomes very young, and yet somehow old enough to remember what it never lived through. That is an astonishing sentence when you think about it. We are old enough to remember what we never lived through. Not personally, not biologically, but scientifically, collectively, perceptually. We have constructed a memory of the deep past out of light. That memory is imperfect, revisable, sometimes frustrating, sometimes full of unresolved notes, but it is memory nonetheless. The first galaxies, the first luminous structures, the first signs of rapid enrichment, the first hints that black holes may have entered the story with more force than expected. These are now part of what the human species can remember. And memory changes feeling. It changes how the night feels when you step outside. It changes what darkness means. It changes what the word young can mean when applied to a universe. It changes what it means to say that reality is stranger than the intuition without slipping into myth. Most of all, it changes how we imagine the path from beginning to now. Not as a smooth hallway, but as a series of thresholds crossed under pressure. The early universe crossed those thresholds faster, rougher, and with more visible consequence than many of us had learned to picture. Webb has given that hidden intensity a face. And in the last movement of this story, the only thing left is to let that face settle into something gentler. To stop asking only what the telescope found, and ask what it means to live in a universe whose first visible light was already working so hard to become the future. It means, first of all, that the future did not arrive gently. The universe we know was not assembled in a calm, patient workshop where each part waited quietly for the next. Its earliest visible light was already labouring, already ionizing the darkness around it, already gathering matter into structures, already participating in a chain of transformations that would, billions of years later, make galaxies like ours possible, stars like the Sun possible, planets like Earth possible, and eventually minds capable of asking how any of this began. That is the most grounded kind of awe I know, not the awe of slogans, but the awe of consequence. A faint early galaxy is not just remote. It is a site where the future was being manufactured. A surprisingly massive early black hole is not just exotic. It is a sign that gravity found ways to become influential sooner than we expected. A patch of cosmic dawn is not just an old image. It is a record of the universe teaching itself how to become visible. And once you see that, the title promise settles into its truest form. The young cosmos was not a fantasy realm with different laws. It was the same universe in a younger, denser, more urgent state, where ordinary physics could produce results that feel extraordinary from the quiet vantage point of the present. A different universe, in that sense, means a different behaviour of the same reality, a different balance, a different rhythm, a beginning less empty, less timid, and more physically ambitious than we were prepared to feel. That phrase matters because feeling is part of understanding. It is possible to memorize facts about redshift, reionization, star formation, black hole growth, and the expansion of space without ever letting them rearrange your perception. But a discovery only becomes fully real when it changes the shape of what seems ordinary. Webb has done that. It has taken a distant, early, abstract universe and made it press against the modern night sky in a new way. The sky above us has not changed. Our honesty about its past has... And honesty is what makes this story so satisfying in the end. The honest version is not that everything collapsed. The honest version is not that cosmology was exposed as fantasy. The honest version is not even that every apparent anomaly will survive unchanged. The honest version is harder, quieter, and better. We built an instrument capable of catching ancient infrared light from the first visible epochs of cosmic history. That instrument began showing us a young universe that often appears more active, more structurally fertile, and more capable of rapid development than many simplified expectations had allowed. It strengthened the case that some early galaxies were already unexpectedly bright. It intensified questions about how quickly black holes could become significant. It helped sharpen the view of a universe becoming transparent through the work of its first luminous structures. And it did all this while the puzzle of cosmic expansion still refused to dissolve into a simple measurement mistake. That is enough to change the air, enough to justify the unease, enough to justify the revision, enough to let a serious scientist say, in effect, that the universe may not be the one we thought we understood quite so neatly. And perhaps the most beautiful part is that revision does not diminish reality. It enlarges it. A smaller story is easier to manage. A larger story is more worthy of the world. The larger story says that beginnings can already contain force, that simplicity at the larger scale can still produce local intensities very quickly, that the first few 100 million years were not a waiting room before the real drama began, but part of the drama itself. That cosmic history did not move from nothing to something in a smooth straight line, but through thresholds, bursts, negotiations, and environmental changes whose traces still reach us. In that sense, Webb has not merely shown us ancient objects, it has shown us ancient urgency. And urgency, seen from far enough away, becomes strange calm. That is what the late universe is, the calm that remains after countless violent acts of formation, collapse, ignition, and transformation have had time to widen into order. We live inside that widened order. The stars overhead seem serene because their deepest prerequisites are ancient. The sky feels spacious because so much of the hard work has already been done. That idea softens something in the mind. It reminds us that peace is not always the absence of intensity. Sometimes peace is what intensity becomes when enough time has passed. The early universe was not peaceful in our emotional sense. It was crowded with first attempts and first successes. The fog of neutral hydrogen did not politely withdraw. It was gradually overcome. Galaxies did not simply appear complete. They assembled in environments full of feedback and pressure. Black holes did not wait for maturity to matter. In some cases, they may have entered the story early and forcefully. Expansion itself was not just a background fact. It was part of the stage on which all these processes unfolded, still echoing into the present through a discrepancy we have not fully resolved. Yet from that compressed beginning came this: a mature sky, long-lived stars, heavy elements, worlds, oceans, biology, awareness. Not because the universe aimed at us. That is not necessary. It is enough that the same reality that formed those first bright structures eventually formed creatures who could look back and recognize that the beginning was already busy becoming. That recognition is deeply calming to me, not because it makes us important, but because it gives us a place that is honest. We are not central. We are not the reason the universe exists. We are not the culmination of a script written in advance. We are something quieter and, in its own way, more moving, a late expression of cosmic history that can remember earlier chapters through evidence. We are present for the unveiling, even if we arrived almost at the end. And what an end to arrive in! A universe old enough to be legible, old enough for light to travel freely across immense distances, old enough for chemistry to have become rich, old enough for a species to build mirrors, cool detectors, launch them into darkness, and use them to ask whether the first visible epochs were harsher, faster, and more alive than anyone had been prepared to feel? The answer so far seems to be yes. Not infinitely stranger, not irresponsibly stranger, but stranger enough. Stranger enough that the night sky should no longer feel like a static backdrop. Stranger enough that young should never again mean simple without hesitation. Stranger enough that the phrase different universe has earned the right to stay, provided we hear it correctly. A different universe not because reality abandoned its laws, but because youth changed the terms of behavior. A different universe because density, timing, radiation, gravity, and black hole growth combined into a regime unlike the one that surrounds us now. A different universe because the first visible light was already carrying more history than we expected. A different universe because the opening act had more momentum than our habits of thought were built to allow. And now, after all of that, the most fitting thing may be to let the story become still. To imagine the Webb telescope far from Earth, cold and patient, collecting ancient light in silence. To imagine that light beginning its journey when the universe was only just becoming visible in the way we now understand visibility. To imagine it crossing billions of years of expansion to reach a machine built by beings who did not exist when it started traveling. To imagine those beings turning that light into knowledge, and that knowledge into a different feeling of the sky. That feeling is enough. A little less certainty, a little more accuracy, a little less innocence, a great deal more wonder. So the next time you see the stars, it may help to remember that the calm above you is late. Hidden inside it is a youth that was brighter, rougher, and more productive than we once knew. Hidden inside it is the evidence that reality began building early and did not waste the chance. Hidden inside it is the strange good fortune that we are here now, small and temporary, yet capable of knowing that. And perhaps that is the final comfort in all of this. The universe did not need to be simple for us to belong inside it. It only needed to be real, and it is more real, more extreme, and more beautifully difficult than the old picture let us feel.